see the screen well, and you can.
Yeah, now it's on the recording, and it is my great pleasure to introduce our first speaker today. He's Kostiv. Is well, one of the top guys and the top superstars here in the PhD program, because he has quite an impactful international publication after the first year of studies at a NATO conference. Which is a little bit more complicating for him is the fact that he's in service. And this is why he was not, unfortunately, able to be here in person. So, Marco, enjoy your life there on the sunny side, and please go ahead. The floor is yours.
Yeah, thank you. Thank you, Vadim, for the introduction. So, as Vadim mentioned, I'm the first year PhD student, and I'm currently serving in the armed forces of Ukraine. Today, we are going to talk about the controllable generation with diffusion models, which has been trending over the last couple of years after the Latin diffusion paper back in 2021. For me to get you to know you a little bit better, to understand how much are you into the topic, the question will be, have any of you gone through the computer vision course in UKU or have the practical experience in the computer vision?
While people are thinking about their answers, I would like to have a counter question for you.
All right.
Are you living 20 days ahead of time?
Oh, sorry, no. Only third one. Yeah, thanks.
That's fine. That's fine.
All right.
I made a mistake, a typical similar mistake yesterday, but I had about a year. So I had something like something of July 2024 yesterday.
Nice. All right, so I've seen one person was raising the hand. We have another person who joined. All right, and we have another person, Charlie, who joined online. Is that the same? All right, awesome. Okay, so there is some experience in computer vision and computer vision course. Awesome. Let's then get down to business and try. If you have any questions or the terminology, please just interrupt me or raise the hand. I'll try to follow or just pick the microphone. Because some of the things that I will mention will assume that you already have some prior experience in computer vision. So what is the plan for today? We are going to talk about what is the variational autoencoder, which is basically one of the ground things behind the diffusion models that make them work so efficiently nowadays. We'll talk why variational encoder is not enough. We'll talk about the diffusion, what is the forward noise process, reverse noise process, why do we need sampler and scheduler, why do we need both, how the latent diffusion works, and then we'll go to the more like state of the art, how the stable diffusion works, how they made the text guidance work, like when you type the prompt and you see the image, how this works under the hood, and what are the ways of other controls, how you can infuse more data into the diffusion process. So to those of you who went through deep learning course or computer vision course, you probably heard about the autoencoder architecture. An autoencoder is a pretty simple and neat idea from back in the days that learns to compress the data into the embeddings. So you have the encoder, then you have the latent representation of an image in our case, and the decoder that reconstructs this image. And it learns by reconstructing its own output, so no labels needed. In the bottom lag, you compress the most salient features, so the most important parts, like you do with the PCA, but not linearly. And this latent space is a handy representation that you can later use for the clustering, classification, compression, whatever else. So our famous MNIST data set where you of the handwritten digits, we know well how to compress the data and reconstruct the information, and it works pretty well. But how do we generate some new information? Like, what are the ways to generate new handwritten numbers, right? It's pretty hard to do that with the autoencoder, because if you slightly shift from the space that we learned, it immediately generates the noise that doesn't look exactly like the real life looking handwritten digits. Like you can compare their constructions and the generations when we slightly shifted the space. And the question is, how can we overcome that and try to get the new ways of writing the digits? And the answer is basically variational autoencoder, which was introduced back in 2013. And that's like important because after that, for 10 years, almost for 10 years, for like 8 years, the generative adversarial networks were the state of the art and nobody paid too much attention to the variational encoder until recent. So it will show you how the space evolved over the time. So the idea behind the variational encoder was that, all right, if we do not map the image to the single latent, but we rather map it to the distribution, and we make the distribution look like normal distribution or like close to normal distribution, Gaussian, with the mu0 and the standard deviation of 1. That will mean that we basically can try to sample later from this distribution and generate the new images. So let's say you have the number 8, it distributes you to the mu and sigma of two vectors, then you can sample from this distribution and get the new number. Two questions arise. First, the sampling operation is not differentiable. So if you just take the random sample, you cannot differentiate that back to apply the backpropagation. And the second one is, how do you make the two distributions look similar? So the first is called the solve to the first solution to the first problem is called a reparameterization trick. So we basically take the mu and we apply the sigma plus sigma multiplied by epsilon, where epsilon is just random noise. And in that case, we actually do not randomly sample. We just multiply our distribution of random digits by the standard deviation, amplify that, and in that case, we basically mathematically it's almost the same as the random sampling and good enough for us to backpropagate the error to through the network. The second problem is how do we make sure that the learned distribution is actually similar to the Gaussian distribution? And we solve that with the KL divergence. So what is Kullback-Leibler divergence? That's basically a measure of how much model probability distribution Q is different from a true probability distribution P. And it goes like those formulas go back to the thermodynamics, and we will not dive deep into that today. But for the intuitive interpretation of those formulas, basically, is from the information theory, is that we look how much information the distribution Q has and how much information the distribution P has. And if we think in terms of the log2, we can basically interpret this as how many bits of information we expect to lose when we shift from one distribution to the other. And this is like backpropagatable, so you can use that as a second term in the loss function along the reconstruction loss and shift the distribution to the normal, to look like a normal distribution. There is a link here which goes deep into the woods how this is how the divergence explains. So if you want to dive deeper after that, so please visit that as well. So once we train this autoencoder, a variational autoencoder, and we'll do that in practice, we can actually see that it produces slightly blurry images. That's one of the limitations of the variational autoencoder. But we can, with this approach, we can actually sample from the distribution and get slightly different looking numbers every time. So the other nice property that arises from there is that since we learn the entire space of the handwritten digits, we can interpolate between the vectors in the latent space and generate the new ways of looking at those numbers. So here is we interpolate through the lambda from number 1 to number 7, and you can see well how the number appearance change. And same if we do from number 9 to number 7. So in the middle, we basically got this like similar to 1, similar to 9, similar to 7 numbers, and this shows that we can actually interpolate through the space. if you visualize or interpolate the entire space that is two-dimensional, you will see how these numbers are nicely grouped together. And you see like the clusters of threes, clusters of ones, the nines, and the digits that looking like between the 1 and 9, 8 and 9, and how you can interpolate between those. If you sample, you get this slightly blurred, but every time you sample from the space, you basically get the unique looking handwritten digit, and you can do this like in almost infinite amount of time. The question is that from this space, what if you want to only generate how the number 8 looks like? What are your thoughts, if you have any? Right. Well, the simplest would be, all right, let's encode the number 8, for instance, and then look at the nearest neighbors. Will that work?
No, I was going to say choose something next to it and try and interpolate to it, which I think is what you're saying as well. Like, I think that'll work.
Yeah, it will to some degree, right? But then what is like, but how much do you want to interpolate, right? Where do you stop? Yeah, that becomes pretty hard. And for this, we introduce the conditional variational encoder. So the idea is that now we can generate the infinite amount of eights, and you do that by concatenating the image with one hot label as input to encoder. We'll do that at the practice. And we concatenate the sample latent with the label as input to decoder. So during the training, we can use the encoder to learn to embed these one-hot encoded labels into the latent space. And then through the reconstruction, we concatenate the one-hot encoded labels with the latents and pass through decoder. So during the inference, we basically can use only the decoder. We don't need the encoder. We say, all right, this is the random noise that we have. This is the label that we want to generate. Now give me back the number which is in the pixel space. And we're training this the same way. We use the reconstruction loss, which usually just MSCL loss, mean squared error plus the KL divergence. Okay. Are you guys familiar with CLIP and how was it trained? All right. So back in the days, I think that was in 2019 or 18, OpenAI introduced a paper called CLIP. And the idea was that based on the contrastive learning, we take internet scale data set of images scraped from the internet and their corresponding captions that we could scrape. And we train the image and text encoder simultaneously. So their embeddings are close in the latent space to each other. So if you say, for instance, the picture of a dog in a green grass, and you show this image, if you encode them both, they will be very close to each other in the latent space. And if you show it like the picture of the dog and say the picture of the cat, they will be far from each other in the latent space. And they teach that in the contrastive learning manner. So they basically simultaneously train the text encoder and image encoder. They pass the positive samples from the scraped images and the negative samples from the randomly taken encodings. And they train a network that can basically find the image or closely looking image from the text description. It's actually used not just in the generation, it's also used in the retrieval a lot. To those of you who will be taking the computer vision course, I remember there was a practice that was about the retrieving the images through the text encodings. But you can think about it as, right, we want to train the network that can predict that the pairs are close to each other or far from each other. So that's CLIP in the nutshell. The CLIP possesses basically the same properties that we've seen in the autoencoder. And those are the faces that are trained with the conditional variational encoder with the clip embeddings as the conditions. So basically, you are generating the clip embedding from the text, and you say that this image has to be wearing glasses, and you can interpolate through the embeddings like we did with the numbers, and get from the image A of this person to the image B where this person is wearing glasses, and you get all of these intermediate steps as well, because you basically know the initial clip encoding, the clip encoding where you want to get, and now you can interpolate through the space. And there is a task of basically generating deepfakes. This was one of the initial approaches, how people did that along with the GANs. But you can still see that the images are a little bit blurry. They have issues with the resolution, and they have problem that basically they average them all into something like very alike looking. So since you're using only the MSK class, eventually you got this blurry like looking images without defined details, and like a lot of faces that just look alike. So that's like one of the limitations that that variational encoders and basically any condition that you apply will still have this issue. Is that clear so far? Just like nod your head if yes. All right, awesome. So what are the VAE limitations? So we got these blurry reconstructions that we mentioned. The pixel-wise MSCA averages define detail. You get the posterior collapse. So what does it mean? That during the training, usually the decoder dominates. It just learns to decode any embedding that you provide into a meaningful image. And this results in that encoder Z carries very little information. So this KL divergence doesn't contribute enough, and diversity drops. So you learn how to reconstruct the images like in the autoencoder, but at the same time, you have the hard time to generate the new meaningful ones. The latent expressiveness. So basically, you try to encode the entire information from the entire image into the single Gaussian prior that cannot model heavy tails. So to those of you who generated like images in the chat GPT and you're writing like the Ostonet cat in the space, wearing the glasses and drinking Coca-Cola, like this part of wearing glasses and drinking Coca-Cola is probably gone because you model this information just in the two vectors, and that's simply not enough. The coarse conditioning is that if you go back to the clip and you say they're wearing glasses, basically, or when you generate the numbers of 8, you just condition this vector only once during the decoding. And usually that's not enough because network tends to forget this information over the time. And the resolution ceiling. So feed-forward decoder struggles with more than 256 to 512 pixels, which is definitely not enough. We have the GANs. At the same time, we had the GANs that were able to generate 4K images easily. And that's why the VAE was forgotten for a couple of years until the diffusion. Diffusion process is basically a Markov chain. This transition operator adds carefully scheduled Gaussian noise plus a matching rescale. So what does it mean? We take the image, let's say the entire image, we add the Gaussian noise, and we added this with alpha, so we are not beyond the 255 pixel space. And basically, every time we add some noise, we are first dependent on the previous iteration, and we are adding the noise to the state when the image is completely gone. You just see like the random noise and you cannot see anything else beyond it. Now, the reverse diffusion process is basically a neural network, but it's the score and the gradient of log density. I will explain what this mean, and not just the sample toward higher probability and shrinking the variance back. So what intuitively this means? You all know what is the gradient descent, right? We are looking for the smallest possible error, and we are looking for the direction on how to minimize the error, like the global minima. In this case, we actually want the reverse process. we want to maximize the likelihood of getting the good looking image, but by every step, and we try to predict the noise that will guide us how to get to this global maxima. So we're trying to predict the score, like how well we are going to reconstruct the image if we predict the noise and apply this noise to the image. So every time you're like, right, this is the direction that you want to take to get from the noise to the image of beautifully looking beach in the mountains. And we do this iteratively like we do in the gradient descent. That's probably the simplest way that we can explain the diffusion process. Again, those terms come from the physics. So if you want to dive deeper in the diffusion process, that's like similar how you were adding the drop of color into the glass of water back in the school. And now the question is like, what should I do to reverse these drop of color from the nice looking clear water and distill it back to the initial state? So how does it work? At every epoch, we basically sample the random time steps because we know the schedule and how much we will add the noise at every time step. We can predict how the image looks like. This is the deterministic process. And we are saying, right, at every time step, we take image xt, we add the amount of noise according to the time step, because this is the deterministic process, multiplied by our Gaussian noise. And at every step, we try to predict the noise and find the loss, which is usually just MSCI, between the predicted noise and the true noise. So we know how much noise we added at the time step t. Now let's predict how much noise was that and try to reverse it back. So we simply like train the network that predicts the noise that is that distance through the ground truth noise is minimal. So as simple as that. And you do that for lots of epochs. Those networks usually take a lot of time to train. And you are, at every time you're sampling like the random images, the random time steps, and train this network like for the noise predictions. Schedule and sampler. So during training, we usually use the linear scheduler. There's also work on the consign, but in the last state-of-the-art papers, they usually use the linear sampler, which works quite well. And I think we'll focus on that and not go into the cosine scheduler. Basically, this is a timetable of how much noise to add at every time step t. And during the inference time, we actually keep the same noise schedule, but reverse it in the bigger hubs in a higher order sampler. If any of you have tried to like play with the stable diffusion, you know that usually it can generate the image in 20 to 30 steps. So you don't actually need like to wait for the 1,000 steps because that's way too long. There is a paper of DPM solver that shows that you can achieve almost the same accuracy in 20 to 30 steps, but much faster. It's basically another timetable that shows you like that we go from the step 0 to step 50, then step 175, step 900, etc., etc. So you don't need to take all of the steps because the network is quite robust at this point to predict noise from any given timestamp. So in the standard diffusion process, question before that, does any one of you know what UNet is? All right, let me draw this for, okay, how can I? Okay, I'm done. So the UNet network was introduced back in 2017, I guess, on the topic of the image segmentation and how this initially worked. So you have this network that is usually the set of the convolution layers. That would be this convolution 1, convolution 2, convolution 3. We downsample this to the bottleneck. And we reconstruct it back to the original image size. And at this point, it looks like the autoencoder. And like the original paper was suggesting, right, this is like the picture of the tree. And this is the semantic segmentation map. Do you know, guys, what is semantic segmentation map? Right. So yeah, basically those were the classification of every pixel, right? So let's say we want to segment the trees. And we were saying that, right, those are all zeros. And when you have the trees, you will get the ones. Basically, you were classifying every pixel. And encoder decoder network was not something new. But what they did, they basically did the skip connections like they do in the ResNet from every convolution to its counterpart. And if we use this conv 2D, here they were using the transpose convolution. Transpose convolution was transpose was giving you ability not to shrink the image into the lower dimension, but actually to upsample it back to the higher dimension. And later on, this was replaced with the upsampling by linear upsampling, etc., etc. But that was the first idea of UNAT. And it feels like quite evident that this is the autoencoder like architecture, but with the skip connections on every layer. And those skip connections basically make the network not to forget about the information that it learned during the downsampling, because otherwise you get a lot of loss of information during the transpose convolution process. So what was introduced in the original diffusion papers, we add the UNAT as this denoising process. So instead of finding the semantic segmentation map, we were actually predicting the noise that we want to subtract from an image. And we were repeating this n times, right? So 1, 2, 3, 4, 5. We got to like 50 or 1,000, depends on your scheduler, and you were constructing back the image. So as you might think of, what are the drawbacks of this approach, like compared to GANs? Please also, guys, if you're familiar with the GANs, not if yes, okay. GANs are another type of network where basically that were suppressing the diffusion for a long time. So you had there were two networks. One is the generator. So let's say it's also UNAT. And you have the discriminator. And this discriminator is just the classifier that was saying whether the image looks realistically or not. So you let's say you are solving the deblurring process or denoising process. So you have the image that has some noise, and you want to output the clear looking image. And you basically do that in a single forward pass through this UNAT. And here you are saying like, all right, what do you think, like computer, whether this image looks realistically or not? If it looks realistically, we'll say 1, and if not, we'll say 0. And basically, you have this game between the generator and discriminator that says, all right, discriminator tries to guess whether the image was generated or the image is from the real life distribution, and the generator tries to trick the discriminator. And like with every epoch, it becomes better and better because discriminator learns, the generator learns, and they compete with each other till the state when the discriminator becomes just too good or the generator becomes too good and it cannot guess anymore whether it was generated or not. So as you can see, here we denoise the image in one single step, right? So you can think about it in a different way. Let's say we are generating the image from the random noise with the condition on the text, and we are generating the image in one single step. So in that case, we can actually do it pretty fast, right? In a matter of a fraction of a second even on the mobile devices. Here, the process is iterative. So every time you need to denoise, you need to reconstruct the image back, denoise it again, again, and again, and again. And this means that the process is quite slow because you're using maybe a smaller unit, but you are doing this multiple times. And as you know, we in the computer science do not to play with the cycles, especially in the machine learning. We like to solve everything in the vector space in one single pass. All right, so this more or less describes why the denoising was slow, why the variational alternate color didn't work well, and why it was suppressed with the GANs for the last almost 10 years. But that was solved. All right, can I clean the... Okay, awesome. That was solved with the latent diffusion. So we know already how we can encode image into the latents from the variational autoencoder, sorry. And we know that basically we can do the same latent process in the latent space. So let's say we are not adding the noise to the entire image. We compress it to the latent space first and then operate in the latent space. And we know that operating in the latent space is much, much faster. So let's say we had the image of 512 as an input, and then we compress this to the image of 64 by 64 by extracting the most meaningful components from it. And the paper was introduced in 2021 that learned well how to do that with the cross-attention unit. So to those of you who are familiar with the transformers, you have the Q key values. We'll talk about this a little bit later. But the idea was that, all right, we predict the noise not in the image space, in the pixel space, but we do that in the latent space, which is much faster because we can now generate multiple forward passes at the time of denoising the single image. And that is basically the idea that is behind the stable diffusion. So we generate the Gaussian noise at first, which is like our let's put it not in this way. Let's put it, we train the variational autoencoder first, and we know how to compress any given image into the Gaussian noise. In the distribution that looks like a Gaussian noise. Then during the inference type, we can sample the new random latent from this distribution of variational autoencoder, and the latency is 64 by 64. And we know that we can encode basically any given prompt into the 77 by 768 text embedding. Then through this unit, we can do the cross-attention between those two parts, the latents that we assume were generated by the variational autoencoder, and the latents that we obtained from CLIP. And we run the multiple steps of the denoising to get the condition latents. So at every step, we're basically guiding the diffusion with the CLIP embedding, and we are predicting the noise to subtract in the latent space. We do this for the multiple steps. Now we get the condition latents, which are the same shape as the input latents. And we can pass it through the variational autoencoder through the decoder part and get the nice looking output image. Any questions here? All right. Let's take a look at the unit. So basically, so you can think about this as the unit that you initially like explained with the convolutional layers. But here we are leveraging the power of attention. So we're basically saying like the query is for this pixel location in the latent space. But let's think about it as the pixel location. Which text tokens are relevant? So if I say I want the nice looking tree in the right top corner of an image, like what are the pixels in this latent that corresponds to the right top corner of the image? What are they relevant? And keys and values supply basically semantic information from the contained prompt that you embedded from the clip. This cross attention by the image latence Q, and the text tokens, they supply K and V. And at every time, they are guiding this denoising process to like basically answer those questions, like where this nice looking tree has to be embedded into the latent, and have to evolve from the like pure noise that we got from the Gaussian sampling to the final nice looking image. Okay, sorry. Any questions here before we go into the guidance? Yeah, go ahead.
I'm confused by step 3, the cross attention, the image latent. What's happening there?
Yeah, so that's not like the step 3. That's the explanation of how the cues and keys and values are connected to each other. So basically, so in the attention in the transformer, right? You got the attention from the like in the classical variation, you got the basically the attention from the different parts of the text, right? So you say that this word has attention with the second word. It tried to build the attention between those. In the cross attention, you basically try to build the attention between the image latence that you embedded and the latence from the clip prompt. So you were trying to match the cues, which is like what in this pixel, what like type of text do I need to generate? Like what this has to be relevant to. So does that answer the question?
I think so, yeah. So it's saying the cues come from the input and which is it attaching to? It's attaching the input to the output, kind of, or transforming, or
So
I'm
not the input to the output, but the both text embeddings and the Gaussian noise are the inputs. You are trying to attach the basically the pixels to the text, to the parts of the text, but not in the space of the pixel of the text, but in the latent space. So you're saying, all right, how do I attach my pixels to the text prompt that was given?
Oh, okay. Wait, Q is just location within the semantic map, and then the key
Yeah,
key and V. Okay, yeah, I got it. Thank you.
awesome. Now let's talk about a little bit on the fine tuning, because it turns out that those large models, which take out billions of parameters, are actually easily fine tunable. Well, not that easily, but still they're manageable. So in the Dream Boost, there was an original paper. I think that was the first one on the fine tuning that was introduced by Google in 2022. They showcase how you can just take a couple of images of the subject class name. So let's say like a dog, and you can fine tune your large network to pay attention to this class and to like generate the unique lookings of your dog from the couple of images. So how they do that, they basically introduce a unique identifier for the object, and then they encode this into the clip. And during the training, they separate the losses of the the images with your identifier and the images from the general distribution. So they mix those like 3 to 5 examples to the larger data set during the sampling of the batches. And they calculate the separate mean squared error losses for the general distribution and the distribution of the images that you cherry picked for your fine tuning. What this results of, because if you just take 3 to 5 images and you start fine tuning the network, it will very quickly disrupt the weights because we will quickly overfit just to predict, just to like generate at every time step your exact image, and it will not generalize. But when we do this simultaneously with the general distribution reconstructions, we make the network not to forget the previous information, but start learning something new. And the question is like just how many times you will show your input example and how do you balance the two losses, right? Because if those like 3 to 5 images just a small part of your entire distribution, will very likely not pay too much attention to them. If you show them too frequent, we will overfit to generate just the images that you have, and it will not generalize. So during the inference, you will not make this dog lay on the beach, because it will forget what the beach is, what is the sea, what is the colorful carpet, etc. So you need to find the balance. And the benefit of this paper is that they showcase how you can sample those images during the data loading, basically in batches, and how can you balance the loss, which is also mean squared error, the loss between the general distribution and your particular identifier distribution, the smaller ones for the fine tuning, to simultaneously learn the information about your dog, and not to forget all of the information that was learned through the training on the internet scale data. The another case is the low rank adaptation, and you might know that from the NLP courses also, if you were attending those or the previous lectures. So the problem with the fine-tuning the entire network is basically you need a lot of memory, a lot of compute, and a lot of parameters, because at every time you need to update, like slightly tweak all of the weights. And usually what happens is that just to like generate the picture of your dog, you do not need to tune like 5 billion parameters or so. You can usually do that with a much smaller scale. And that's why when the LoRa was introduced. LoRa is used both in the computer version, also in the natural language processing and LLMs. But the idea is that you add a tiny tweak to the weights. For each weight matrix W in the pre-trained model, LoRa computes new weight, which is weight plus BA, which typically adds just 1% of the parameters. You freeze all of the weights, you just slightly tweak them, and this is enough to learn the new styles, and this is enough to try to fine-tune network for your particular use case. The nice thing about it, since it adds only 1% of the weights, it's pretty easy to train, because you don't need a lot of backpropagation steps. You only backpropagate through those like small number of ways, because you freeze everything else. And the second one is that you can plug and play lots of different styles on the run, because you can load them in the memory or unload them. You don't need like, let's say the stable diffusion is like a couple of gigabytes of the weights, and LoRa is just like 200 megabytes. This means that you can plug and play them and load into the memory fairly quickly. And you might see that in the different apps that are generating the images of the different styles. Basically, they do this small sample, like usually like 250 to 200 images with the text descriptions, and they only tune the LoRa weights, so the network does not forget everything that it knew before. All of the original weights are frozen. You add only some minor tweaks to them to generate the unique looking style. The next one is everything played with LoRa? Sorry. All right, awesome. Let's talk a little bit about the control net. So in the original Stable Diffusion paper, you only have the text to image, and the text to image is usually not enough for the generations, because you cannot like control them too much. For instance, you cannot provide the shape of the object or the position of the object, or even or if you like try to generate people, their pose estimations is also pretty hard. Like, let's say that you want to generate the person who is taking 20% of the image and raising both of their hands. Just doing that with stacks will be completely overwhelming and hard to achieve. And that's when the control net was introduced. So it basically allows you to add more conditions to the generation. So in the previous two setups, we were only adding the conditions for the text. So we still had the same shape of the network. We only were tweaking how we interpret the text and embed this into the clip embeddings. Here we basically allow to add the new, completely new looking inputs. That can be anything. That can be another image, that can be a signal, that can be another like text, like whatever you choose. The idea is that we log all of the parameters in the stable diffusion and we clone them into a trainable copy to the control net side. This copy is then trained with external conditional vector and the original weights are frozen. And the reason why creating the weights, the original weights rather than training the entire network from like fine-tuning the entire network with additional inputs is actually to prevent the overfitting, but the data set is small. And it's recommended that you can train the control net with as much as 50,000 images, which is much more than LoRa and DreamBoost initially required, but that actually provides you much more information and options to operate with. So in this case, let's take a look at what this does. So you have this image of an elk. You extract the edges from it. You embed the edges into the latents of the same shape as the initial latent input from the image. And you basically create the copy of this UNet network where you like concatenate the inputs from the control net network and the UNet network, and you like do the skip connection between them. We'll look at the architecture a little bit more detailed, and you generate the final inputs like the images of an elk, which have the similar properties of the edges. So you can see that the position is similar. The size is similar, but now you can generate the elk in the different environments, backgrounds, etc. And the elk is also every time is a little bit different. So you see, like in before that, we only have this part where we insert the prompt, timed, and the latent input. And by adding the control net, we can basically allow to have the additional input of the same dimensionality that the latent input was originally given. The nice looking trick here was, I think that was the first paper that introduced the zero convolution. So in the original, so we don't copy all of the layers, we just copy some of them. And the layers for the decoder, we apply them as a zero convolution. So what this means, we basically initialize all of our kernels, the filters with the zeros at first. And this is done so we progressively learn the weights over the time and not disrupt too much the initial weights that we copied for the encoder. So if we just copy everything at once, we'll like very likely quickly overfit to have the same distribution as the stable diffusion. But if you like progressively adding those weights to the zero convolution to the kernels, we can learn over the time and increase their ability to steer the diffusion process, basically. So think about this as the learning rate scheduler, right? While you're training the deep learning networks, you often apply the trick of learning like rate scheduler, where you use the pre-trained models first. You apply very small learning rate for the first couple of epochs, and then you gradually increase it to disrupt the weights more and more and more. So this basically, this is almost the same, but we keep the learning rate constant in this case, and we are actually playing with the kernel weights, and we slightly increase their amplitude over the time. So again, how the entire process works, just repeating one more time, we have the control net and UNet that have skip connections that are mentioned right here. We are connecting one to the other, and we are embedding the input condition, which is in our case are the are the edges into the latent space of the same shape as our input was. And this every time we basically steering the conditioning and the diffusion not just with the text prompts, but also with the additional inputs that we've added. And for instance, those are examples of the different inputs that you can provide. So you can like map the sketches to the images. You can provide the normal maps to the images by and saving the 3D representation, the depth maps, canny edges that we just discussed, just the lines, edges, semantic segmentation maps, and human poses. The nice thing about it is that basically if you have the nice estimation for the human pose and you have the bunch of images with the text descriptions, you can generate almost infinite amount of the training samples for it, and you do not need to label this every time. So how this usually works, you take the state-of-the-art model that generates the depth maps. You can get or generate the prompts for the images, and almost immediately you have a nice looking data set, which is not that noisy and learns to generalize well because you already have the trained stable diffusion weights, which are very powerful and can provide a lot of information. And the control net allows you to add the new inputs that can be used, for instance, to preserve the identity of the object. So here you generate the Jordans on the different backgrounds by keeping the Jordans intact. And you can try to squeeze the information about the brand in it. Implement, for instance, embedding. So if you like go back here and you say that right now I want to learn how to generate the in-painting image, you can basically provide here the mask of the region that you want to in-paint, and you can apply this kind of processing. So in case of the in-painting, you would keep the original image here. Now you will have the mask, instead of this image, you would have the mask of the region that you want to in-paint. And you could learn how to in-paint the images without having to retrain the entire network, but just adding the new mask as an input. Now, finally, there are questions, how can we evaluate those models? Have you heard about perceptual distance back in the days? So the perceptual difference is basically I take the VGG network, I extract the embeddings from the network, and I compare my generation to those embeddings, and I say how much perceptual information I still keep about this particular generation. The problem is that when you try to generate the new images, you cannot use the perceptual difference because basically you don't have the ground truth images, right? Because every time we sample from the Gaussian distribution, the image will be looking slightly different, so the features will not align, they will look differently, etc. So with the fraction inception distance, it basically measures the similarity between the distribution of real images and the distribution of the generated images by comparing the feature vectors extracted from the inception between network, but it does that similar to the KL divergence, right? We compare how similar the distributions are. And the lower FID scores indicate that the generated images are closer to the real images in terms of the visual features. So instead of comparing them one by one, we create those like distributions of all of the images from the real world sample and from the distributed sample, and then we try to compare the distributions. There is a clip score, which measures how well the generations align with the original prompts. We have the clip pre-trained, and we just like find the distance between the embeddings and how close are the embeddings of the generated image to the original prompt encoded by clip. But what works best, to be honest, is actually the human preference test. It measures what actually looks and fits the prompt better. So you just create this A/B test of multiple images generated by two networks. You show both of them to your annotators, and they vote what looks better and connects to the prompt better. At this point, we are out of slides. Do you have any questions so far on the variational autoencoders or the diffusion process? Okay, cool. Then I propose to take 15 minutes break and continue at 11:15 with the practice. Sounds good?
Thank you very much, Marco.
Thank you.
Yeah, you are the boss. You declare the break. We never be the break, and that's it. It's like you're in an army now. That's fine.
Right. Let's do the 15 minutes if students agree. I think that will be enough, and we'll do the practice and finish a little bit sooner.
Okay, fine.
Cool.
Enjoy the break
Yeah, thank
on the sunny side.